Hey everyone, welcome to homework 3.5. Today we are looking at continuation of our exponential functions. And so we're going to start with a population of butterflies. Before I do that, I'm going to go over one thing about this. I just want to make sure that you have a second chance to hear it from me, right? Your function is always going to be your original value times the factor that you're multiplying by, to the power of time, or to the power of your input. Almost always that is going to be time in these scenarios. That's usually what we're measuring over. As I've stated, the input is usually time, but you're always going to have your original value times the factor times to the power of time. And then the other thing to remember is if they give us a percent increase or decrease, we have to create the factor. If it is an increase, we're adding plus the rate, so plus the percent or fraction in decimal form. And if it's decreasing or decay, it's 1 minus the percent or fraction. Okay, and that creates then our factor. The other thing to keep in mind is that you can find your factor from a table by dividing a later value in a consecutive y output, dividing a later value over an earlier value, and then that will tell you, right, because you're dividing, how much you would multiply by each time, which then gives you your direct factor. Let's go ahead and take a look at the first one. A population P of migrating butterflies satisfies this equation, where W is the number of weeks since they began their migration. So here we're multiplying by 4/5, so I see that I'm multiplying by a number smaller than 1, which tells me that instantly I am going to be looking at decay. The population is decreasing or dying off, right? So at the first week, or sorry, at the start rather, the original value is 100,000. And then after the first week, it's going to be 4/5 of that, or 80% of that. So we're going to go down to 80,000. And then each time I'm multiplying by 4/5 or by 80%. And so we'll get 64,000 times 0.8, 51,200. And then our last one will be 40,960. All right. So then it says graph the butterfly population. Think carefully about how to choose the scale for the axes. So here I would recommend that you go by 10,000s. So 10,000, 20,000, 30,000, 40, and it should just fit to 100,000. 70,000, 80,000, 90,000. And then this is 100,000. And then going across, we're looking at 1, 2, 3, 4. We could go by ones because we're looking at weeks. All right, so at the start, it's at 100,000. So at the start, we start up here. At 1 week, it's at 80,000. At 2 weeks, it's at 64,000. At 3 weeks, it's at 51,000. And then at 4 weeks, it's at 40,960, so close. So notice that we start to see this curve. It's no longer a straight line, it's curving. And if we were to continue to plot, right, it would continue that curve. It says, what is the vertical intercept of the graph? So the vertical intercept is 100,000, or 0, 100,000. And this tells us at 0 weeks, or at the start, it is, a population of 100,000. About when does the butterfly population reach 50,000? So approximately, right, we're looking at between 3 and 4 weeks here. Because we assume that between 3 and 4 weeks, right, it goes down from 51,000 to 40,960. And so sometime between those weeks is when our butterfly population hits 50,000. The graph shows the amount of chemical water in a sample. It is decreasing exponentially. Find the coordinates of the points labeled A, B, and C. So because we know it's decreasing exponentially, we know that the factor is the same each time. In this case, our factor can be discovered by putting 800, making a ratio of the value after 1 hour over the original value, which is also going to give us 0.8 or 80%. And so that means that each of these values is 80% of the one before. So if we make a table, remember that's our friend here, we're starting at 0 and 1,000, 1 and 800. And so then 2 would be multiplying 800 by 0.8, which is going to give us 640. And then multiplying that by 0.8, and it will get 512, right? So this is the first 2 points that they give us. This is point A, B, and then C is at the 4th hour. And so after 4 hours, 512 times 0.8 gives us 409.6. Okay, so our points A is 2, 640. Point B is 3, 512. And point C is 4, 409.6. And you can see that this point is just above the 400 mark, right? So it kind of gives you an idea of where these points are and makes a lot of sense there. Number 3 says this graph shows the amount of chemical in a water sample at different times after it was first measured. Select all statements that are true. So let's look at this. So first of all, looking at this, we know our starting amount is 2,000. That we can for sure tell. But the rest of these points are kind of between. We could guess that this is maybe at 1,000. But here, we can't really tell exactly what that is. So I do want to note that we can't tell exactly what the points are. So it says the amount of chemical in the water sample is decreasing exponentially. It does look that way. However, because I cannot check the factor and I cannot check to see that the factor is the same each time, I can't with certainty say that. Same thing with B. It could be decreasing exponentially. We're not really sure. It does look like it because it has a curve, but because I can't see if that factor is the same each time, I can't know for sure. So there, C, it's not possible because we can't tell the exact numbers. We can tell that it was first measured. There were 2,000 milligrams of chemical in the water sample. We can see that on the graph there. After 4 hours, we could estimate this, but we can't know this for sure. So that one would also not be 100% true because we could maybe guess that that's where that point is, but we don't know for sure. Number 4, the graph shows the amount of chemical in a patient's body at different times measured in hours since the levels were first checked. Could the amount of this chemical in the patient be decaying exponentially? Explain how you know. So again, I'm going to look at the ratio of the amount after 1 hour over the original amount, and this is going to give me 0.6 or 60%. So after 1 hour, 60% is left in the body or 40% decayed. So the way I would know if this is decreasing exponentially, or way I could check, is I can say 360 divided by 600, right? So this later amount by this earlier amount, because they are consecutive one after the other. And this would also give me 0.6 or 60%. So from what I can tell, the factor is decreasing at the same rate and therefore exponential. So we would say yes, likely, because the factor is the same. We could also say that the decay rate is the same, right? It is decreasing by 40% each time, leaving us with 60% each time. Number 5, the height of a plant is 7 millimeters. It doubles each week. Okay, so that tells me 7 is our starting. We're doubling each week. And so this would be 2 to the power of time, okay, or W weeks. So it says, which represents the height after 4 weeks. So this would be 7 times 2 to the 4th power. So we're looking for anything that is equivalent to this. So this is not true because that would be 15, and that's not the same amount. This is the exact one that we got here. This is not the same because this is 7 to the 4th power, and we're not exponentially multiplying by 7. We're exponentially looking at the doubling per week. Here, this is the same as 2 to the 4th power, so this is accurate. And then this is 2 times 4 can be broken into 2 times 2, so that's not quite. We would need another multiplication by 2. So not that one. All right, number 6, the people who've read a new book is 300. It doubles each month. We're going to finish the table. So 600, 1200, because it's doubling, 2400, 4800. What do you notice about the difference in the number of people who have read the book from month to month? So it is increasing, right? So here we're adding 300. Here we're adding 600. We're adding 1200. So that amount that we're adding each time is increasing. But the factor is I'm multiplying by 2 each time. So the factor is times 2. It says at the beginning of the month, n people have read the book. How many people will have read the book at the beginning of the next month? So this would be 2n, right? So at 1 month, the following month, whatever that amount is, then it'll be double that amount. Number 7 is a review. And so it says solve each system of equations. And this first one is easy to solve because we see right here we have opposite coefficients. And so I can eliminate immediately with that one. So let's try x plus y equals 2. Negative 3x minus y equals 5. These cancel out. X and negative 3x is negative 2x. And then 2 and 5 is 7. Divide both sides by negative 2. We get x equals negative 7 over 2, or negative 3.5. And so then, to figure this out, we're going to plug it back in and find y. So negative 3.5 plus y equals 2. I'm going to add 3.5 to both sides. And we'll get y equals 5.5. So now we have an x value and a y value. That's 5. For this next one here, it's not quite so easy, but we do have an opposite sign of coefficient for y. And so what I'm going to do then is try to eliminate the y values. I'm going to do that by multiplying this whole thing by 2. Because when I do that, I'm going to get 2 times 1/2 x is just x. 2 times positive 2y is positive 4y. And then 2 times negative 13 is negative 26. Then we get 2x, these cancel out, equals 8 and negative 26 is negative 18. Yes, okay. And then divide both sides by negative 2. We get x equals negative 9. Once you have that x now, you can plug it back in and find y. So if you're listening to this, your job is to find y and tell me what that is and fill that in here. Your homework code word today is firehook. Firehook is your code word for today. Make sure to write that back up here at the top where it says homework code word. And then let's go back and look at this last part of the classwork in case you did not get to it. So I'm only going to go over this part right here, but it says state whether the graph shows exponential growth, decay, or neither. So here our graph is going down and it is at a curved line. We can't tell exactly, but we can assume that if we assume that these are all exponential, right? This is going to be decay. Then this one going down is also going to be decay because it is going down. This one right here, number 3, goes down and goes back up. So this would be neither because we have both a decrease and an increase. And then number 4 appears to just be increasing. And so that would be our growth. Here we're looking for whether it is growth or decay. And in order to do that, you need to look at the factor, this part right here only, okay? And so in looking at this factor, it is 1/5, which is smaller than 1, which means that it is decay. For number 6, we have a factor of 1.234. This is the factor, even though there's no coefficient here, because this is what is being raised to a power. And so that is greater than 1, so this is growth. We can assume then that the original value was 1, right? Because that's the invisible number in this scenario. For number 7, we have 0.47 as our factor. That is smaller than 1. It is a decimal, and so this would be decay. And then number 8 is tricky because the coefficient is a decimal, but this here, 8 over 3, is a fraction that is greater than 1, because that would be 2 2/3, right? And so that's greater than 1. So as we multiply this, we get bigger. So this one Number 8 is actually growth. All right. If you have any questions or you need any help, you know how to reach me. Happy homeworking, and I'll see you tomorrow.